Hello! It's been quite a few weeks since the last video, and that's because it took a little while to get the latest project to a level where I'm happy to share it. But here it is. In this video, we're building a digital spectroscope. It's a do-it-yourself kind of spectroscope. We are repurposing components that weren't really made for the job. So it's not going to be as accurate as commercial devices, but we're going to calibrate it as much as possible. So it should give a decent output. What we will need is a camera which is capable of taking raw pictures, a pocket spectroscope, like this, a way of connecting the two, and a piece of software that I wrote over the past weeks. So initially, I wanted to use this monochrome Canon 350D, which I converted a few months ago. But I want you to be able to reproduce this project at home without too much effort. And if you've seen the video about the monochrome conversion, then you know that it's quite a tedious process. But I think I came up with a decent way of doing it with a camera that has its color filter array intact. I'll give you a brief overview first, and then we'll look at the details. So the first step is to connect the spectroscope to our camera. And for that purpose, I designed and 3D printed this connector, which you can slide on like a lens hood. I realized that not everybody has access to a 3D printer, but any way of connecting the two in a sturdy way will do. Then we take a raw image of the spectrogram. Why not a JPEG? You probably know that on top of the sensor in your camera, there are some micro lenses and there's a color filter array. For example, this is the X-trans pattern used by the Fuji cameras that I'm using. This is a Bayer pattern, which is used by most other manufacturers. And the colors that you see here indicate that only reddish, greenish and bluish lights can pass through the filter at the respective photo sites. So at each photo site of the sensor, we get either a red or a green or a blue signal. But a picture requires red and green and blue components at each pixel. So when you take, for example, a JPEG, then the missing values are estimated through some clever form of interpolation. This interpolation is called demosaicing, and it uses information from adjacent pixels to find the missing values. But we don't want information from adjacent columns of our spectrogram to be mixed, because they relate to different wavelengths. And close to the spectral lines that we want to see, the signal can change quite strongly. So combining the signal of different wavelengths can reduce the resolution of our spectrogram. So we're not taking a JPEG because we don't want any demosaicing or any other changes of the sensor data. One more point about this. You can see here that each column of the X-trans pattern contains pixels of all three colors, whereas a column in the Bayer pattern only includes two of the three colors. That makes it a lot easier to use the X-trans sensor data for our spectroscope. To use pictures from a Bayer sensor, we'd have to think of something to get a signal of each color at each wavelength. So as of when I'm filming this, I've only implemented the code for the X-trans pattern. Okay, we've got a raw picture of the spectrogram. To be able to use it, we need to calibrate our setup. First, we need to extract the red, green and blue signals from the image. The first step in the calibration is then to figure out the mapping of X coordinates of the image to wavelengths. Once that's done, if we were using a monochrome camera, then we'd be almost finished. But we're not using a monochrome camera in this video, so we have to figure out how the red, green and blue signals of our picture relate to the amount of light that came in at each wavelength. So we'll use a light source with a known spectrum to figure out how sensitive our setup is to light at different wavelengths. So we're measuring the spectral sensitivity of our system. Maybe let me try to be more clear about what I mean. Imagine that light with this spectrum reaches the outside of our spectroscope. And you notice that the maximum here is 1. And that's because we don't actually care about how much light comes in absolute terms. More light means brighter and less light means darker. What we do care about is the relative amount of light of one wavelength to the other wavelengths. Okay, so light with this spectrum reaches the outside of our spectroscope. Then the light has to go through the spectroscope, through the lens, and through the color filter array. Everywhere along that path, some light can get reflected or absorbed, and some of it will pass through. Once the photons reach the sensor, they have to knock an electron out of its place on the sensor. Otherwise, they are not registered when you take a picture. So, of all the light that reaches the outside of the spectroscope, only some of it will contribute to the signal that we measure, and how much varies per wavelength. And we are looking for the function that takes us from the light to the measurement. We can find it by dividing the measurement by the light source. Once we know the spectral sensitivity, our calibration is done, because then we can point our camera at an arbitrary light source and obtain the spectrum of light by dividing the measurement by the sensitivity curve. Since we have three signals, red, green and blue, we get three estimates for the spectrum of the light source. Each of them will only be accurate in the part of the spectrum where the particular color has a strong response. So in the end, we'll have to combine the responses appropriately. So that's the idea, which is quite simple. But the difficulty is usually in getting the simple ideas to work well. So let's get to it. I'm going to use my X-T2 for this project. And the first step is to pick a lens that will focus the light that comes out of this analog spectroscope onto our sensor. The choice of lens is important. Let's start with the focal length. My camera has a resolution of 24 megapixels, which means that there will be a lot of information, even if the spectrogram doesn't fit the entire image. So even if we use a wide-angle lens. Lenses are usually at their sharpest in the center of the image. As you move away from the center, all sorts of errors and aberrations start impacting your image. You can correct a lot of those in software, but I'd rather minimize them in the first place. So I'm using this 23mm lens, where the spectrogram is relatively small and near the center of the image. You've probably seen that the spectrogram is not perfectly in the center of the image. And that's not because I mounted it off center, but it has to do with how these spectroscopes are built. I've actually mounted it at an angle to move it more towards the center, although I overdid it a bit. Next, we're going to pick an aperture. This lens is very fast. It can open up to f1.4. But which aperture do we want to use? Let me show you how the image of the spectrogram changes as I change the aperture. We're starting wide open and we close it down, one stop at a time. You can see that the part of the spectrogram that is clearly visible becomes smaller and smaller. So what's happening? To show you what I think is going on, let's briefly look at how a lens works. This is a vastly simplified representation of what's really happening, but it should be okay for our purpose. On top, where it says source, is a point that we want to photograph. And under normal circumstances, especially outdoors, light from all directions hits that point and gets at least partially reflected. So the light that comes off that point also travels in lots of different directions, and some of it reaches our lens. The lens then changes the direction of the light so that all the rays reach the sensor at pretty much the same spot. And that happens for rays that originate on a source point that's along or very close to the central axis of the lens. For example, this is another point that's still close to the axis. In both cases, you can see that not all rays make it to the sensor, because the aperture stop blocks some of them. When we close down the lens, so when the aperture becomes smaller, then more light rays get blocked. And in this case, that's not really a problem, because there's still plenty of light coming in through the center, and you can compensate for the light that gets blocked by leaving your lens open for longer. But the situation changes a little bit with the spectroscope mounted to the lens. Now there's a slit, and it splits up light per wavelength. For example, let's assume that greenish light of some wavelength passes through the slit at the axis of the lens. Unlike before, the light of this wavelength travels almost exclusively along this one ray that's shown in green. The other rays that are shown in orange are not really used by light of this specific wavelength. Now, let's look at another wavelength. Remember the second source point we used before. Let's assume that reddish light of some wavelength gets diffracted by the slit so that it travels along this particular ray that's shown here. Of this wavelength, almost all light will travel along this path, and almost no light will travel along the other paths shown in cyan. So if we close down the aperture now, then the path of the red light will be blocked. Before, without the spectroscope, we could make up for the blocked light by leaving the lens open for longer. But now, almost all light of that wavelength traveled along this path, and almost no light through the center. So leaving the lens open for longer won't really help, because there's no other path that light of this wavelength takes. So we effectively lose information about light of this wavelength, as we saw in the images before. Of course, there is a downside to using a very large aperture. When you close down, so when you use a very small aperture, then each point on the sensor can only be reached by light that comes from a very narrow set of directions. When you're wide open, the light from many more directions can potentially reach that point. Normally, without the spectroscope, that manifests itself by a little bit of blurriness. In our case, you wouldn't really expect this to be an issue, unless there is some additional light inside of the spectroscope, which would then pollute our measurements. I haven't really talked about how these diffraction spectroscopes work, but they're not like a prism where all light just gets split up into a narrow set of angles. I don't really want to go into the details in this video, but there's certainly a chance that some additional light reaches the sensor, which can affect our results. Okay, we've got the focal length and the aperture, right? We're using the widest aperture we have. Regarding the ISO, I'm using the lowest native ISO that I have available, because I don't want any unnecessary noise affecting our measurements. And that just leaves the shutter speed, which we can set so that our image of the spectrogram is relatively bright. Once we've created the connector to mount the spectroscope to our lens, we can take a picture of the sky. Before I forget, if your camera has image stabilization, turn it off. I spent about a day looking for an error until I realized that I forgot to turn off image stabilization. And as a result, the location of the spectrogram on the images was changing a little bit all the time. But that little bit is enough to mess up your readings. In fact, even with image stabilization turned off, when taking lots of pictures of the sky, the image was still moving a little bit on my X-T4. So I ended up using my X-T2 instead, which doesn't have image stabilization. Okay, so we've set up our camera, the spectroscope is mounted on it, and we've turned off image stabilization. Now we have to focus our camera. I found the best place to focus is the area of the spectrogram where red turns to green, including the lower or upper edge of the spectrogram. In my case, that gives a focus distance of 0.5 meter. And once that was set, I turned the camera to manual focus so it doesn't try to refocus all the time. It's time to take the first picture. It's a bit difficult to judge the brightness of the spectrogram, so I often do some exposure bracketing. With exposure bracketing, the camera takes multiple pictures at different shutter speeds, and in at least one of them, the spectrogram will be well exposed but not blown. Let's have a look at the picture. To process it, we're going to use a piece of software that I've written. First of all, you'll notice this white rectangle. We'll use that to tell the program which part of the image it should use. But the first step is to set up the black levels. You know, the signal for our images is created when photons knock electrons out of their place on the sensor. And those electrons are then measured, and the measurement is then converted to a digital value. But electrons can also leave their spot if no photon hit them. So there will be a signal even if no light came in. And we have to tell the program how strong this minimum signal normally is. This information is usually given in the EXIF data of your image, but it's not always in the same format, so the program is not reading it out automatically. For my X-T2, the black level is 1019. So the camera is a 16-bit camera, which means that the raw values are between 0 and 16,383, but anything that's around 1019 can be considered as no signal. Okay, I've added an option for lens corrections, but the spectrogram is very close to the center of the image, where the image is normally very accurate. So these corrections don't do very much, so I'm going to skip them. By the way, these options are used throughout the entire program. The two below are just for visualization on this tab. So for example, we can only show the green values. It's also easier to look at the image when we set the black level for visualization a bit higher. Okay, we've got the image and we can already see some dark lines. Let's look at one of the columns in more detail. By moving the dashed line, you can tell the program which column of pixels you want to look at. And in the next tab, all pixels along that column are plotted along the horizontal axis. Ideally, I'd expect every pixel in this column to have the same value. But they don't. What's going on? My first thought was that this light fall off looks like some kind of vignetting. In photography, lenses are often brighter in the center and then gradually get darker towards the sides. But the lens that I'm using here doesn't suffer from much vignetting so close to the center. So I thought maybe the optical elements inside the spectroscope experience vignetting. But when I took some careful pictures of a halogen lamp, I got this result. Vignetting doesn't just go away, so this is not due to vignetting. But you know, there are lots of other effects, and you may have heard of the cosine 4 law. I don't really want to go into details in this video, but it has to do with light that reaches the sensor at an angle being weaker than light that reaches it from straight ahead. So I say that this is due to the cosine 4 law, but of course we need to test if that's actually true. So I wrote this little helper program where you can load an image and fit a cosine 4 function. And as you can see, it fits really well. But the really important question is whether this light fall off affects only the vertical direction, or if it also affects all other directions, including the horizontal axis. Because if it is radially symmetric, like it would be in a regular camera and lens, then the wavelengths that are away from the center would receive a weaker signal, not because there is actually less light, but because of this cosine 4 effect. So in that case, we'd have to correct our measurements for this effect. But given the way in which diffraction spectroscopes work, I think the effect might only affect the vertical axis. An easy way to test it is to apply both kinds of corrections and look at which result is more consistent. The difference will be most visible far away from the center. So this is the vertical correction and this is the radial correction. And the vertical correction looks much more consistent, which is good because it means that we don't have to do a correction. We can get away with picking a narrow row of pixels where the values are relatively consistent and we take their average. So let's do that. Here it looks like the range from 1800 to 1900 is relatively consistent. So now we can look at the entire spectrum and we can already see the location of some spectral lines. The thick red, green and blue lines you see here are the average values of the row of pixels we chose before. The thin lines indicate the 90% confidence interval, so they show the variation in the values along the vertical axis. So if the range we chose before wasn't very consistent, then we'd see a large uncertainty here. Okay, we've got the first rough idea of the spectrum. But when I first saw this, it looked like this. The resolution didn't seem to be very good. For example, compare it to these measurements where the lines are much more defined. You might think that that's due to the blurriness caused by large aperture, but it's not. Both of these pictures were taken at f1.4. The difference is that in the second picture, I put a black tube in front of the spectroscope. And that helps because light of some wavelength that reaches the spectroscope at an angle is not diffracted to the same location as the same light that reaches it from straight ahead. So there is some mixing of wavelengths happening. And with this tube, we can limit the angles from which the light reaches the sensor. So we can already see something that looks a bit like a spectrum. We do see some spectral lines, but we don't know the wavelengths where they occur. Right now, all we see is their pixel locations on the image. And that's what the third tab is for. It allows us to map the pixel coordinates to wavelengths. And this is actually quite simple. All you have to do is familiarize yourself a little bit with the sun's spectrum. And quickly you will identify some of the most prominent spectral lines. For example, the first line on the left is the F line, which is at 431 nanometers. The third one is the G line at 486 nanometers. I put a link to the common spectral lines into the video description. Diffraction spectroscopes like this one should split wavelengths in a linear way, so 2 points should be enough to get a good mapping. But I think it's better to map more points and to check if they are actually linearly spaced. That's what the fourth tab is for. On the horizontal axis we see the pixel coordinates, and on the vertical axis we see the nanometers that we've just mapped. The orange line is a linear fit through the data points that we've mapped, and it looks like a very good fit, right? It's pretty much linear. So we can move on to the next tab, where we can finally see our measurements at the corresponding wavelengths. If we were using a monochrome camera, then we'd be almost finished. I say almost, because there is one more effect that we would have to consider. And that's that the diffraction gratings that are used in these spectroscopes don't transmit all of the light that comes in to the spectrogram that we're seeing here. Only some part of the light goes into this spectrogram, and how much varies by wavelength. It's called the efficiency of the grating. So wavelengths where the efficiency is lower will receive less light than those where the efficiency is higher. And if we don't correct for this effect, then our results won't be super accurate, even if we're using a monochrome camera. You should be able to get the efficiencies from the manufacturer. I did ask the producer of this spectroscope, but so far I haven't received a reply. In our case, it's not actually that important to get the grating efficiencies, because since we're using a camera with a color filter array, we have to calibrate the relative strength of the red, green and blue signals anyway. And this calibration will also take care of the grating efficiency. Okay, let's move on to almost the last part of our calibration. Right now we've got 3 signals, red, green and blue. And we can see the locations of the spectral lines, but we're not actually having a proper spectrogram. To obtain that, we're going to use lamps whose spectrum we know, and will compute how our system reacts to the light that comes in. For example, this is a halogen oven lamp with a color temperature of 2500 Kelvin and a CRI of 100. A color temperature of 2500 Kelvin means that the radiation that it emits is similar to that of what's called a black body with a temperature of 2500 Kelvin. A black body is an idealized concept in physics, but incandescent and halogen lamps are actually very similar to black bodies. And the radiation of a black body is given by what's called Planck's law, which we can easily visualize. I also said that the lamp has a CRI of 100. The CRI tells you how close the light actually is to the given color temperature. So it sounds like we know the spectrum of this lamp perfectly, but unfortunately we don't. The color temperature is normally rounded to the closest 100 Kelvin, and the CRI is usually given within a range, so it may not be exactly 100. Also, the way in which the CRI is computed is not actually by directly comparing spectrograms, but by comparing how the light appears to our human eyes. So by using these kinds of lamps, we'll probably get a rough but not a perfect calibration. By the way, I'm not using LEDs for this calibration, because their spectrum is usually quite steep and spiky. Steep slopes like we're seeing here make it much more difficult to get good results, because even small inaccuracies can lead to large errors. So let's take a picture of the 2500 Kelvin lamp and see what we get. By the way, taking a picture of this lamp wasn't as straightforward as you might think. Pointing the camera directly at the lamp didn't give super consistent results. I ended up bouncing the light off this color checker. You know, a color checker is designed to reflect light without changing it. Other surfaces, even if they appear white, normally absorb some of the light and therefore change the spectrum. So I wouldn't use, for example, a piece of white paper or a white wall. Better use a color checker. Right, let's load the image into our program and see what we get. You probably notice that the sensor values go towards zero quite rapidly at around 425 nanometers, which doesn't match the spectrum that we plotted. And that's because the lamps in our homes normally have some UV filters, which block light below a certain wavelength. And it looks like that's approximately 425 nanometers for this lamp. So I'll cut the spectrum there. Since we know the spectrum of the light that came in and the signal that we measured, we can now compute the spectral sensitivity by dividing the measured values by the target spectrum, which gives us these three curves. I've also got two different lamps with color temperature 2700 Kelvin. One is an old one that I found lying around. The other one I just bought last week. If you do the same for them, then we get this curve. That one is different to what we got from the first lamp. And I think that happens because we don't know the exact spectrum of the lamps. We just took the blackbody spectrum of the rounded color temperature that's written on the packaging of the lamps. They won't match perfectly. So it's not surprising that we get different response functions. So now I'm explicitly assuming that the response curves of the 2700 Kelvin lamps are correct. And I'm making that assumption because these two lamps, even though they were produced a few years apart by different manufacturers, give quite consistent results. And I think in the absence of more information, that's the best I can do. To tell the program to use one or more response functions, just press the Use checkbox. By the way, the response functions look quite noisy, but we can average out a lot of that noise by taking multiple pictures and combining them. Okay, let's save the calibration and go to the main program and test it out. First, we'll load the signal of the 2700 Kelvin lamp, which should be very accurate because we used it to create the response functions. But you can see that there's something going on with the blue signal. And that's because at these high wavelengths, both the blue signal and the blue response functions are very small. So even small inaccuracies can lead to large errors. And therefore, for each color, we're only going to use the part of the spectrum where the response function is not too small or not too steep. Back in the calibration, we can set the range where the response function of each color should be used. We can either set a hard boundary by just entering one value, or we can fade them in and out over a range of wavelengths. At the end, our final spectrum will be a mix of the predictions of the three colors, and this fading leads to a smoother transition. I'm using these values here. So if we go back to the main program and reload the settings file, then we get a much nicer spectrum. Now let's load an image of the sky. It's not actually too bad, but there is something wrong. The spectra produced by the red, green and blue channels don't match perfectly. Why would that be? Well, I can think of a few reasons. The major points are probably that throughout this process we're making measurement and other small errors, which accumulate. The polarization of light has an impact on the efficiency of the diffraction grating. Earlier you probably saw this circle around the spectrogram in the image, which I've ignored, but which may affect the results a little bit. And also, we've created the response functions from a single lamp whose color temperature we don't know exactly and which has a very different color temperature from the sky. Right? So there are bound to be some errors. We can try to ameliorate the last issue by adjusting our response functions. So the last thing I'm going to do to try to improve the results is to use a little bit of machine learning. Rather than using the response functions we computed before, I replaced them with a neural network. And I initially trained that network to give an output that's similar to the response functions we got earlier. That's just an initialization. So our main training process starts from a reasonable state. Then I train the network, which changes the response functions, so that two criteria should be optimized. The first is that for the 2700 Kelvin lamp, the spectrum that's predicted based on the measurements matches the blackbody spectrum. This first criterion is identical to what we did before. For the second criterion, I took a lot of pictures of the sky, and I required the model to give the same result, the same spectrum, for the red, green and blue channels. And that should take care of the gaps we see in this image. Of course, if there are some errors in our data, if our color temperature of 2700 Kelvin is not correct, then we won't be able to satisfy both criteria perfectly. But hopefully we get a decent result for both. If we want to, then we can prioritize one of the two criteria by giving it more weight in the optimization process. So after running this for a few hours and adjusting the training parameters a few times, I got these response functions. Let's import them into our calibration so we can use them. For the 2700 Kelvin lamp, the results are not as perfect as the way before, which is expected because we use this lamp for the calibration. But apart from a little divergence towards the edges of the individual colors, the results are actually quite consistent. Now let's look at an image of the sky. This is an image that was not used during the training or validation process of the model. So it's completely unseen data. And again, the results are quite consistent. For our final spectrum, we average the individual colors with the weights we set earlier. And that's it. This should be a decent estimate of the actual spectrum of light when the picture was taken. It's not perfect, but I think that given that we're using components that weren't made for this purpose, I think considering that, our results are actually quite good. What do you think? Whew. That was a lot of work. There are so many things to figure out. There are one or two more things that I'd still like to improve. One is that during the optimization process, instead of prescribing a color temperature of 2700 Kelvin for the reference light, I want to make the color temperature learnable. The result should still have a blackbody spectrum, but the color temperature should be unknown. I'll post an update when that's done. So I'm going to take a brief holiday, and when I'm back, I'll either make the second part of the history of light. If you haven't seen the first part, do check it out. I think it's really cool. Or I'll move on to the next project, which is probably going to be about 3D scanning. So it's about creating a 3D model of a real-world object by taking lots of pictures of it. And I'm planning to build a rig and maybe some software for that. Also, from now on, I'm going to split up the projects into smaller parts, into multiple videos, because I think that makes it easier for me to produce and for you to watch. Let me know what you think. So, thanks for watching and see you soon.